Alright, in today's video we're going to take a look at the topic of significant digits and simply how to count significant digits when you're given a measured quantity. Significant digits are also known as significant figures, and they apply to measured quantities, so measurements. Suppose we have this pad of post-it paper and we're wondering how wide is the paper. So let's grab a ruler and we'll measure the width in terms of centimeters. So I'm going to line up the left-hand side of my paper there, and now let's take a look at the right-hand side, and let's try to figure out what the width of this paper is. Well, we can see that it's clearly past 10 and not yet 11, so if I were recording the width, I might start by saying 10. I'm sure of those two digits. And then if we look very closely, you can sort of tell that it is past the first tick mark, so it's past 10.1 centimeters, but it's not yet past 10.2 centimeters. So I'm sure that it's between 10.1 and 10.2 centimeters, so I'm very sure that it's 10 and 10.1, and now what I'm going to do is very carefully estimate how far it is between 10.1 and 10.2. And to me, it looks like it's a little bit closer to 10.1, so I'm going to say it's about 10.13 centimeters wide. Now that's a valid way to measure and express the measurement of this piece of paper. And let's just think about what we just did. We knew from the ruler that it was past 10 centimeters. In fact, we knew that the width was greater than 10.1 centimeters. So we were sure of the first three digits in that measurement. Those three digits were certain. The last digit was an estimation of the distance between the 10.1 and 10.2, and if somebody else thought it was 10.14, somebody else thought it was 10.12, we wouldn't argue with them because we know that we're just estimating that last digit. So what we have here are three certain digits plus one uncertain digit, one estimated digit. That's how you record measurements in the lab. You record all the digits of which you're certain, plus one extra digit of which you are uncertain, which is being estimated. If you've ever used an electronic balance, perhaps a centigram balance with 2 decimal places, you might see on the screen of the balance a number like this. It might say that something has a mass of 123.2, and then it's a centigram balance. There's one more digit. But if you ever used an electronic electronic balance, you know that this last digit tends to fluctuate. One moment it looks like 26, the next moment it's a 25, the next moment it's a 27, and then it's back to 26. It's constantly changing. So when you record the mass on this electronic balance, you are certain that it's a 123.2. You're certain of those 4 digits there. And then this last digit, which is fluctuating, you would estimate. You would perhaps wait 10 seconds and then look and record whatever you see. But that last digit is going to be an estimated digit because it's fluctuating. So we record all of the digits which are certain plus one digit which is estimated or uncertain. When you do that in a measurement, you've recorded all of the significant digits in that measurement. Would it make sense to you that if I were trying to record the width of this paper, if I used a ruler like this, would it make sense to you that to record that the width is 10.1279 centimeters would be silly? There's no possible way to get all of these extra digits from this ruler here. You cannot be that accurate in measuring with this ruler. 10.13 was possible because we could be certain of the 101, those first 3 digits we were certain of, and this last digit, this one last digit, we estimated. But here we would have been estimating all 3 of those digits, and that would be silly. So you have to think about the number of digits that you can use when you are recording a measurement, and that's what significant digits is all about. Now, often you're given in a problem, in a word problem in science, you might be given a measurement. And so that measurement will have the significant digits already, and you just have to count them. You have to look at a measured quantity and count how many significant digits are there. And so there's a set of rules for doing this, and they can be a little bit complicated, but let's try to work through them relatively quickly. So the easiest thing about measurements when you're trying to figure out how many of the digits are significant is that non-zero digits, any digit from 1 to 9 in the recorded measurement, can be assumed to be significant. So if you see 129, you can be sure that all three of those digits are significant. In the measurement 0.48, we'll see in a little bit why this first zero is not considered significant, but the 4 and the 8, because they're non-zero digits, they're definitely significant, so that number has two significant digits as well. Right now you're probably wondering why the 0 did not count as a significant digit. Well, zeros are the confusing things when it comes to significant digits, because sometimes they count as significant digits and sometimes they don't. If you find a zero in between non-zero digits, so zeros that are between significant digits, they'll always count as being significant. So 5,007, we know that the 5 and the 7 are significant, they're non-zero digits, so therefore the zeros in between them will count. So when zeros come in between non-zero digits, they'll always be significant. So that number has 4 significant digits. In the number 0.508, we have this 1 0 at the front, which again is not going to be significant, and we're about to see why in just a moment. But this 0 is in between the 5 and the 8, so this 0 will be significant. So 508 has 3 significant digits. In 40.032, the 4 starts off as significant, the 3 and the 2 are significant, so the zeros in between will count as significant digits, so that number has 5 significant digits in it. Trailing zeros, zeros that trail or end the number, are significant if they come after the decimal point. Okay, so if trailing zeros are after a decimal point, they're going to be significant. So 2.50, the 2 and the 5 are significant because they're non-zero digits. This trailing zeros at the end of the number is significant because it comes after a decimal, so there's going to be 3 significant digits there. 3.0000, all 4 of those zeros will count as significant digits because they come after the decimal point and after a non-zero digit. Okay, now that's important. They have to be after a non-zero digit to be considered a trailing zero. So there's 5 significant digits there. 124.0, the 0 comes after non-zero digits, it's a trailing 0, and it's after a decimal point, so it counts. There will be 4 significant digits. Leading zeros, those are the ones we saw up above in those other examples, are not considered significant. They're considered to be just placeholders. Okay, so they're not significant. So a leading 0 is a 0 at the start of a number, whether it's before the decimal, 0 point like this, or even right after the decimal. If they come before non-zero digits, if they're leading zeros, they don't count. So 0.025, neither of these zeros is significant because they're leading zeros, so just the 2 and the 5 will be significant, 2 digits. In this number here, none of these zeros at the beginning are significant, they're simply placeholders, and then the 1 and the 0 will be significant at the end, 2 significant digits. 0.001025, the 3 zeros at the beginning are leading zeros, they don't count. The 1025 has 4 significant digits. Now, there is one set of numbers which are unclear technically, and that's whole numbers that end in 0. So if you have a number like 6,000, it's unclear whether or not any of those zeros are significant, whether they're all significant. Maybe just the first one is significant, maybe just the first 2 are significant. We can't tell from looking at that number. Some people play a game where they say, some textbooks will claim if there's no decimal place at the end of the number like this, then we would ignore all of those zeros. And they would say if there is a decimal place at the end, then we'll count all of the zeros. I don't like that little game, because although it solves the problem when there's only one significant digit in this case, or all of the digits significant, it doesn't help me distinguish if only one or two of those zeros will count. A better way to do it is to convert the whole number to scientific notation. If 6,000 was meant to have just one digit significant, the 6, we could write it as 6 times 10 to the 3. And now the 6 has only one significant digit. When you're looking at scientific notation, times 10 to the 3 is not considered to be part of the significant digits. If you meant the 6 and the first 0 to be significant, so only one 0 significant, then you could write it in scientific notation as 6.0 times 10 to the 3. And now it's clear that that 0 is significant, because as we saw in our third rule, if you have a trailing 0 after a decimal, it is significant. If you meant the 6 and the first two zeros to be significant, then in scientific notation, 6.00 times 10 to the 3. And if you meant all of the zeros to be significant, 6.000 times 10 to the 3. You can always switch numbers into scientific notation. You can always do that. But with whole numbers, it's a good idea to do it. Okay? Finally, there's a set of numbers that we call pure numbers, and they have infinite numbers of significant digits. They're not actually measurements. So for example, when you see a formula for circumference of a circle, circumference equals 2 pi r, the number 2 in that formula does not have just one significant digit, because it's not measured. It's not as though the formula might actually be 2.01 pi r. It's exactly 2 pi r. So because that number 2 is an exact number, a pure number, not a measured number, it's considered to have infinite significant digits. Okay? Let's try some examples. You have this in your science booklet on page 20. If you've already done it, you can check some of your answers. Otherwise, let's just try a few of them together. So in this measurement here, we have 1, 2, 3, 4 digits which are definitely significant because they're non-zeros. And then the 0 at the end, because it's a trailing 0, will count. So there's going to be 5 significant digits in that measurement. In the second measurement, none of the zeros at the beginning will count because they're all leading zeros. Zeros at the start of a number are never significant. The 5 is definitely significant, and the 0 that comes after the 5, a trailing 0 after a decimal, will be significant. So there's 2 significant digits there, the 5, 0. 7.090, the 7 and the 9 are definitely significant. The 0 in between them is significant. And a 0 that's trailing after a decimal also is significant. There's 4 significant digits there. Scientific notation, 3.00 times 10 to the minus 7. This number, the times 10 to the minus 7, is ignored for significant digits. If you think about scientific notation, that just tells you where the decimal was moved, so it's not significant here. 3.00, though, has 3 significant digits. Those zeros do count because they're trailing zeros after the decimal. So 3 significant digits. 0.1000. The 0 at the beginning is a leading 0, does not count. The zeros after the 1 are trailing zeros after a decimal, so they count. So there's going to be 4 significant digits there. 16.00 has 2 non-zero digits which will be significant, and then 2 zeros which are trailing zeros after the decimal. That has 4 significant digits. They all count. 1.0 times 10 to the 10. This is a scientific notation example. The times 10 to the 10 is not significant, but the 1.0, both of those digits are significant because the 0 is a trailing 0 after the decimal. 0.0013, none of the starting zeros will be significant. They're leading zeros, so the 1 and the 3, there's 2 significant digits. 1.2000 times 10 to the 6. The times 10 to the 6 is scientific notation, does not count. But the 1.2000, the 3 zeros, will be significant because they're trailing zeros after the decimal. There's going to be 5 significant digits in that number. 0.0000102000. None of the starting zeros will be significant because they're all leading zeros. The 10200, all of those digits will be significant. This zero is significant because it's between non-zero digits, and these two zeros are trailing zeros after the decimal, so they also count. So there's 5 significant digits there. 1500, now this has a decimal place at the end, so I can tell that this is meant to convey all of those digits are significant, as we discussed earlier. If there was no decimal point, then it would be unclear. It would be unclear whether or not it was just 2 digits, the 1 and the 5, 3 digits, the 150, or 4 digits, 1500. The best thing to do would have been to write that in scientific notation, and now it's very clear that the 2 zeros are significant. But putting a decimal at the end like that was a way to communicate that all of the digits are significant. 17.8, 3 significant digits. There's no zeros in there to worry about. 0.002, the zeros are all leading zeros, so none of them count. There's only 1 significant digit. 9050 is significant here. The zeros at the beginning are leading zeros and do not count, so 9050 has 4 significant digits. Now sometimes you've done a calculation on a calculator, and your calculator will display a number, and then you're going to have to round off the answer to have a certain number of significant digits. So let's see how to do that. The first couple of examples are relatively easy. 6.16782 is on my calculator screen, but I need to round it off so it has only 1 significant digit. Therefore, just the 6 is going to be my significant digit. I'm looking at the digit that comes next, 6.1. The 1 is less than 5, so I'm going to round it off to just say 6. 2 significant digits, so I'm going to keep the 6 and the next digit. But when I look at the digit that comes next, I see a 9. That tells me to round the 1 up. So it's going to become 6.2. Now this next one has a typo. It's missing a decimal point, so you can insert a decimal, 0.00197872. I need 2 significant digits. None of the leading zeros will be significant. So 0.00 digit. That's what I have to have. So since I need to keep 2 digits, I'm going to look to the 3rd digit to see how to round up or round down. In this case, it's an 8, so I have to round up the 19, and it's going to become 0.0020. Okay, 20, because I'm trying to keep 2 significant digits. 3.14146 times 10 to the 4, I need 4 digits. The times 10 to the 4 is not part of the significant digits, so 3141, there's 4 digits. Look to the next digit, it was a 4, so I'm going to keep the 1. I'm not going to round it up, I'm just going to leave it like that. So 3.141 times 10 to the 4. 213.25, I need to just have 2 significant digits. Now there's going to be a problem here, because keeping 2 significant digits, you might think, well, then we'll call it 210. But now we have a whole number that ends in a 0, and as we discussed, it's not clear whether or not that's 2 significant digits or 3. So let's switch it to scientific notation. 2.1 times 10 to the 2. Now it's clear that it has 2 significant digits. 17.163000 with 3 significant digits. 171, there's 3 significant digits. The digit that comes next is a 6, so I'll round the 1 up. It'll become 17.2. 90210 needs to have 3 significant digits. 123, So we're going to have to switch this again to scientific notation to be clear. We'll call it 9.02 times 10 to the power of 4. Now it's clear that it has just 3 significant digits. With one significant digit, again, we'll have to convert this to scientific notation, right? Because if we write 200, it's not clear whether or not it has 1, 2, or 3 significant digits. But to say 2 times 10 to the 2, it's now clear that it has 1 significant digit. All right, I'm going to stop there. I hope that helps you. You can finish off this worksheet, and we're going to have a little quiz soon on Edmodo on significant digits, counting them. We're also going to start learning in class how to do calculations with significant digits, adding, subtracting, multiplying, dividing measured numbers, and how to round off our answers appropriately.